Okay, so till now, when we have started discussing about testing, we have been discussing testing of combinational circuits. Today we are going to consider the testing of sequential circuits. When it comes to sequential circuits, there are many testing techniques which have been used or which have been proposed. So they relate to, for finite state machines, circuits which are primarily implementation of FSMs, we can use state table verification. We will discuss a little bit about it. Random testing, transition count testing, scan based testing, signature analysis. So in this, presently, as far as the real circuits are concerned, complex VLSI circuits are concerned, these two are the preferred testing modes. But it's interesting to know that actually some of them actually also use the fact of random testing and transition count testing as part of it. So we will very briefly discuss it. We will also briefly discuss state table verification, which is very nice from the point of view of analysis, theoretical analysis, and also as we have discussed the state machines, and we also discussed reduction of states in state machines. But unfortunately for very large state machines, this is not applicable. It's, let's say, very cumbersome to do state table verification, though the testing like this, if you can really verify state tables, then you can really have a lot of confidence on your circuit. But the time that may require to generate the test vectors and also to perform testing is rather large. Let us look at what is the problem in state table verification. Primarily what we are interested in is, we want to verify each transition. How do I verify a transition of the state machine? So I have to by first taking the machine to a specific initial state, applying the input to perform the transition, and then verifying the final state. So if you have a state machine which is, let us say, state Si, and you apply some 0, it gives an output of 1 and it is Sj. If I want to verify that this particular transition occurs, what do I have to do? I have to somehow, wherever the machine may be in any of the initial states, I have to take it to Si, and I have to have a confidence that I have reached Si. Please remember, we are working under a condition that the machine may be faulty. Okay. So I have to take the machine to state Si, and at least I have to apply, we will talk about, I have to apply some input so that the machine reaches Si, and I have confidence that it has reached Si. Then I apply the input. When I apply the input, of course I can monitor the output, but this output may be the same not only for 0 input, but for 1 also it may be the same. So I cannot still say with confidence that the transition is verified, because this Si may be going to Sk. So just looking at the output, though I apply the input 0, basically even at 0 the faulty machine may be going to Sk instead of Sj. So then I have to verify that I have reached state Sj. So the three things have to be done. First, take the machine to the initial state to verify the transition, apply the inputs to perform the transition, then verify that the machine has reached the final state. So if I can be sure that machine reached the initial state and the machine reached the final state, then I can verify that this transition has occurred. And this has to be done for each of the transitions. So this is the mechanism that is used for state table verification. Verify each transition by first taking the machine to a specific initial state, applying the input to perform the transition, and then verifying the final state. For this purpose, we need two in sequences. One is called a homing sequence, another is called a distinguishing sequence. We have studied about distinguishing sequence before, so today we will talk about the homing sequence. Let me first define both of them. Homing sequence is an input sequence, is said to be a input sequence is said to be a homing sequence for a machine if the machine's response to the sequence is always sufficient to determine uniquely its final state. I apply it. So basically what I say is, I look at a machine can start from any state. Machine can be presently in any state. I have a specific pattern of input. I apply that input sequence. What I am allowed to do is only monitor the outputs. By looking at the outputs, I can be sure that the machine has reached a particular finite state. What it implies is, if you look at the black box, This is my state machine. I am allowed to apply some input and I am allowed to monitor some output. So, this is my state machine. I have a, so the machine could be in any one of the states that I have. It is in this state, it could be A, B, C, any state that I have. So, I apply this input sequence and I am only allowed to monitor the output. By looking at the output, I can be certain that if, let us say, the output pattern is a certain pattern, I can now be certain that if I receive this particular output pattern, the machine has reached state D, for example. I do not have to be sure about the starting state, I only have to be sure about the final state. So, that is about the I should be sure, I should uniquely be able to say that, okay, looking at this output pattern, there is a unique output pattern for any of the output states that it needs to reach. Okay, so, actually more than one pattern may map to an output, that is a different issue, but I should be able to distinguish when, let us say, my final state is D or final state is C, the output should be, pattern should be mutually exclusive. So, that is called a homing sequence. And we will see that how we can find homing sequences. Well, now let us define a distinguishing sequence. This is something which we have already seen before, because distinguishing sequence is an input sequence which when applied to a machine will produce a different output sequence for each choice of initial state. Please remember, when we are doing the state reduction problem, this is what we are trying to do. What we are trying to do is go through the, we have clubbed all the states together and then we are trying to apply the output inputs so that I can distinguish between states. Where did I start from for each choice of initial state? Please remember, what is the problem in reduction? If there is no such distinguishing sequence exists between two states, that means those two states can be collapsed into one state. There is no input sequence exists by which I can distinguish between two machines, identical machines, one starting from state A and one starting from state B. If I cannot distinguish between them by any input, that means these two states are, one is redundant, you can collapse them and merge them into. This is what we did in state reduction. So, distinguishing sequence we define. So, an input sequence which when applied to a machine will produce a different output sequence for each choice of initial state. If you now look at the distinguishing sequence and homing sequence, every distinguishing sequence will be a homing sequence, but not vice versa. The way it occurs is, if I know where I started looking at the output, I know which initial state I start from, I can also predict what final state I am going to. After all, I know the input sequence, I know the initial state, I can perform all the transitions. I am right now assuming a correctly functioning machine. If the machine is functioning correctly, I know what initial state I started from looking at the output, and then if I can know what the initial state, I can always predict the final state because I know what the input has been applied and how the. So, distinguishing sequence is a homing sequence, I can get the final state, but every homing sequence is not a distinguishing sequence. Because I can predict the final state, now it is not necessary that I can always predict the initial state I started from, because two initial states which lands up into the same final state need not be distinguishable by a homing sequence, because only I need to, here I have to be uniquely be able to identify each input state. Here I am only saying that I should be able to identify the final state. So, but multiple input states by this particular homing sequence may land up in the same final state, and I have to have only a confidence that which final state I have reached. Looking at the output, I should be able to. So if you look at it, distinguishing sequence is a homing sequence, but not vice versa. We will not talk about the distinguishing sequence any further. You should go back and refer to what we did in terms of state reduction, and this is basically the same thing that we are applying. So, but let us talk about the homing sequence. So, let us say take a very simple state table. So, there are 4 states A, B, C, D, and so some outputs are specified. So, this is your present state, this is your next state, and Z, and So now let us look at, so what happens over here is I am only allowed to monitor the output, just like in case of either distinguishing or homing, nothing else. About the states I should only be able to distinguish. Now let us see this homing sequence tree. So what happens over here is I start from, this is called the uncertainty vector. ABCD is uncertainty vector, basically is I don't know where the machine is. So I be able to distinguish which final state I am going to. So let us say I start from ABCD, I apply 0. If I apply a 0 input, looking at the output, I will be able to say, looking at the output, I will be able to say I am in either in state AB or I am in state D. If my output is 1, my final state I know is D. If the output is 0, I know that my final state is either A or B. But if I apply the input 1, I will not be able to say what my final state is, because final state will be ABCD, it can be anything. So this is how this uncertainty vector is getting refined. So you start from this and then you refine it. So when you apply 0, so I can look at the output. For AB I am getting an output of 0, for D I am getting an output of 1. Say, unlike for example in distinguishing sequence I also had to talk of CD, okay, here I don't have to, because my final state is what? But if I am 1, I am getting an output of 1, I am certain I have reached the state D, okay. So that is what by applying an input of 0. Now I can again do that, I can either apply 0 or 1 again. If I apply 0, what happens? I reach the final state of AB, AB will remain AB. And D will remain D, and within AB I will not be able to distinguish, so this uncertainty ABD. And this is a terminal node in this tree, because I have not done any refinement over the previous. This uncertainty vector is same as this uncertainty vector. These elements are called homogeneous elements or trivial elements. If there is only one element, it is a trivial element. Homogeneous means all the states are the same, okay. So you can write it as DD also, okay, C and D both reach DD. So when it comes to, these are non-homogeneous, if there is no refinement in the non-homogeneous part of the vector, that means I reach a terminal state. Non-homogeneous, more than one state. So AB and this AB and this AB is same, so I cannot now refine anything further, applying 0. But if I apply 1, what happens is, let us say if I apply 1, what happens? So if I apply 1 here, then I reach output state of DB, and if I apply 0, I reach C. Sorry, if I apply on D, I reach C, apply vector of 1. So AB gets done to BD, and D gets, so there is not, it is not one-to-one correspondence, I am just writing it in the sequence which is alphabetic sequence. So BD, AB goes to BD and D goes to C. Now when it reaches BD, now if I apply 0, I will be able to distinguish whether I reach the final state A or final state D. So because so I get this final state A, D, D. BD has become A, D, D. If I apply 1 on BD, so I reach BC, and on C I apply, I will reach A, so it is BCA. Of course, one could have gone ahead, because this is still not a terminal node. The reason it is not a terminal node is, this is not same, the non-homogeneous part is not same as the previous node. But there is no need to go, because this is, I reach this, which means that this is a uncertainty vector which is acceptable to me as for generating the homing sequence. I have only either trivial components or homogeneous components. All these components are just only one state, or all, if they are more than one state, all the states are identical, so that is homogeneous. So in this case A, D, D, so this is a, this particular uncertainty vector gives me that I reach, so I do not have to, otherwise I can refine this further. So I get a homing sequence now 0 1 0. So what happens when, what is the meaning of this homing sequence 0 1 0? So once I reach this, so 0 1 0 if you apply, let us see what happens. If I am in state A, I can start from A, B, C, D. Any of these initial state I can start from, and I can apply 0 1 0. If I apply 0 1 0, A 0 will take me to B. So output is 0 0 0. So 0 1 0 application will be, output will be 0 0 0, and once this output is 0 0 0, I know what state I have reached. Now if I look at, if I start from B and I say 0 1 0, so 0 will take me to A, this one will take me to D, and I will, so 0 0 1, and I will go to state D. And so now let us look at C. So when I look at start from C, so I would 0 will give me an output of 1, and 1 will give me output of 0, 1, and I will reach a state. And now the last one is D. So D, if I apply 0, so that is, will give me output of 1, and then I go to state D. So I apply a output, so I get a C. C, I go apply D. Okay. So now see here the outputs, these two outputs are same. I don't know where I started from. So this is the reason it's not a distinguishing sequence. But I don't have to, I only have to, by applying this input 0 1 0, there are only two final states, either A or D, and I should be able to distinguish it whether I am reaching A or D. If my output is 0 0 0 on the pattern 0 1 0, I know that I reach state A. If my output is any one of these two, 0 0 1 or 1 0 1, I know that I have reached state D. And so this is the homing sequence for this particular pattern. It's not a distinguishing sequence because looking at these outputs, I will not be able to distinguish between whether I started from state C or state D. Output is the same for state C and state D. A distinguishing sequence should be able to distinguish between these two. Okay, so anyway, so you can perform this analysis that we did for partitioning and get a distinguishing sequence. So I skip that as a work for yourself because we already done it in some manner. So let me just repeat what we are said over here. So we start from, so the process is, I may be in some initial state. First of all, I have to somehow reach SI, and I have to look at the output to be able to reach SI. So now I apply a homing sequence, okay, but what will happen is, if the homing sequence is applied, I may, because the homing sequence is not going to give me all the states, I may still end up in some other state. Of course, I have a confidence in saying that I have come to this state, but this state may not be the same as the SI state. So of course, then I have to apply a pattern and assume that these transitions are correctly getting executed. Or the other method is, first verify this transition. Start from where you reached. For example, in this case, let us say this is state D as far as the previous sequence is concerned. Verify this particular transition. How do I verify this particular transition? I apply the homing sequence, reach D, apply the input required to perform the transition. I reach a final state over here, and now apply the distinguishing sequence here. So once I apply the distinguishing sequence, I will know that what is the initial state I started with. Let us say this was a transition which was going from D to some state, let us say A. These are the transitions. So, I reach D through a homing sequence, apply the inputs required to perform the transition, and then once I reach there, I applied the distinguishing sequence and verified that I started from state A. Once I had done it, the homing sequence transition plus the distinguishing sequence will be able to prove that this transition is working correctly. There are of course some assumptions that we are making here, that the faulty machine does not have more states than the machine which we have designed. Okay. So, the number of states do not increase. If the number of states increase, then this mechanism will not work, because then the behavior could be completely erratic. Because whatever all your homing sequence and distinguishing sequence is designed with the view to the states that you have in your machine. So, faulty machine should also have the same states. Only possibility that we allow is the transitions that are occurring may not occur correctly in the faulty machine. They may not match exactly the transitions that are there. So, apply the homing sequence, get to a node, and once you have verified this, then you can, for example, as I said, you cannot reach by homing sequence, you cannot reach arbitrary states, you can only reach certain states through the homing sequence. For example, in the example that we took, the homing sequence always reached either A or D, you only reach A or D. So, if I had to verify a transition which starts from state B, I cannot first do it, I had to verify first transitions which are start from states A or D, and then proceed in that manner, sequentially take up one transition by. Once that transition is verified, then homing sequence for this particular state will become the homing sequence for D plus this input, because I already verified that this transition is occurring correctly. That way you can generate a homing sequence for all the states. Again, one assumption is your state machine the nature of the graph is such that all the states are reachable from all the other states. You reach any state, there is a path available, there are a set of transitions available to reach any other state. So, under these two assumptions, it is possible to correctly exactly verify your state machine transition by transition if you can derive first the homing sequence and the distinguishing sequence. Of course, we know that a distinguishing sequence will exist if there are no redundant states. And we also know that a distinguishing sequence is a homing sequence. So, basically for any state machine which has no redundant states, you can actually derive both a homing sequence and a distinguishing sequence, and once you can do that, then you can verify that the state machine is correct. Okay. But the overhead, you can see that why in practical situations this is going to be a problem. Assume a machine which has say 50 states or 60 states. It is going to be extremely complex, because your homing sequences and distinguishing sequence, to test each of the transitions that are present in that machine, you have to apply so many input vectors, so many inputs, first homing, then input, and then distinguishing, and you have to do that for each of the transitions. So, the test pattern that is required to test it in this manner becomes very complex, but once the machine is tested like this, so actually what happens is very critical state machines have to be tested in this manner, because the cost of the testing is not, but where you really want to, then you have this approach. Okay. So, I will strongly advise you that just to look at the distinguishing sequence that we talked about before, and use that and apply it, take a small state machine and try to generate maybe even just 3 states and generate a test pattern for verifying each state transition. Okay, so that was the first method, and now we take up the other methods, the random testing. The idea of random testing is basically like this, that you have a random pattern generator, and now you have a good circuit and a circuit under test. So, this is when you have one copy of the circuit, which is in some manner it has already been verified, either exhaustively or applying a lot of test inputs and so on and so forth. You already know that the circuit is functioning. Then what you really need to know is you put the circuit under test and known good circuit, apply the same pattern, and the length of this pattern, if it is longer, your confidence level on your circuit will be larger, depending on how big a pattern you apply. and remember it is a sequential circuit. You can do the same thing for any combinational circuit as well, but combinational circuit is, because typically for the number of inputs it is possible to use the regular test pattern generation methods we talked of, but for sequential circuits it becomes very complex to do it. So for that we can apply this random method and compare the output. If you look at this, what we are doing is we are applying a random pattern generator, and because if this is actually a really truly a random pattern generator, then I need a good circuit. If it is not truly a random but it is a pseudo random pattern, what is a pseudo random pattern? Pseudo random pattern, you start from a seed and it is predictable. The numbers that are going to be generated are predictable, that is why they are pseudo, but the numbers are not correlated, and this sequence, if the pseudo random pattern generator, it will of course repeat sometime, but if it repeats after, let us say you are only interested in 100 random numbers to be generated, and if it repeats after 1 million and the numbers that are generated, the consecutive numbers are non-correlated, they have a random behavior, whatever. If it is a uniform random, then in the range that you are considering they are uniformly distributed, then such a sequence generator is called a pseudo random sequence generator. So each time I am going to start my test with the same seed, I know that exactly the same set of random numbers will come, but they are random because they are not correlated with each other. So that is the, so such are called PRBS generators, pseudo random binary sequence generators, and they play a very critical role in testing today. Later on we will see that how these are adopted for testing, especially all the built-in self-test is based on these pseudo random sequence generators. PRSG or PRBS, both are sequence generators. The binary sequence generators are called PRBS. So now, so if you have a pseudo random, so instead of a random pattern generator you replace it by a pseudo random sequence generator, so then you do not really need a good circuit. You can replace this good circuit by expected pattern result. When you are making your device, where do you get a good circuit? Because you are doing it, especially in a VLSI type of an environment, all these things are done at the design stage itself. You are generating your test patterns and so on. So you do not really have a good circuit with you. Okay, so to be able to test, okay, once you have done mass production you can do that, but at the initial stage it is not possible. So what you do is, so what you want is you want the expected result, and if you can compare with the expected results, then you can say that the circuit is fine. But how do I get the expected result? If I know that what the pseudo random sequence generator is going to generate, I can compute the value of the output, whatever transformations this circuit is doing. I can compute the value of the output and store it in there. So this is simulation. I simulate the circuit, get the results and store it maybe in a ROM or maybe in some storage devices, and compare the result that is coming from here with the result that is stored in the storage device, and then if these two match, then I declare that the circuit is functioning correctly. So this thing works. So random testing, and this is also called random testing, but of course it is not truly random because it is a pseudo random generator. The problem with this method is that if this lengths had to be long, of course if it is a complex circuit I have to apply a lot of test vectors. See, please remember one thing, when we are doing combinational circuit testing, we did a lot of analysis to do fault coverage and so on and so forth. Either for the test patterns, if you are doing fault coverage, then you can say that okay, even with a limited number of inputs, I can be sure that I am going to cover a large number of faults. But when you are applying random inputs, then you do not really do too much of, you cannot do too much of analysis of fault coverage. You do not really have too much control over what the next input is going to be. They are randomly distributed, okay, with some logic by which they are generated. So what you do is, so you try to cover more faults by applying more test vectors. So if you apply more test vectors, you assume that more faults will be covered, and also they are random test vectors. But if you apply more test vectors for a complex circuit, the result that needs to be stored is also rather large. And if the result needs to be stored, within the circuit, as in case of built-in self-test, where the circuit stores the result also, then it's, you need to compact, you don't want to store a lot of, see, testing is always considered an overhead. You are doing a design and you have to say how much overhead I can have for testing, how much cost I can have for testing, 5%, 6%, 10%. But if this ROM is going to be very large, then this is going to be extremely expensive and take a lot of area of the circuit itself. So you try to minimize this. One of the ways of minimizing people introduced was what's called transition count testing. Here, for all the inputs that you are applying, you don't store all the corresponding outputs. But if you look at the output, and if your output is 0, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1. There is a transition that is occurring here, there is a transition that is occurring here, transition occurring here, transition occurring here. So you identify the transitions. So 1, 2, 3, 4, 5, 6. 6 transitions are occurring and you just store the number 6. So you do exactly the same thing as you did in random testing, either from estimation, either from expected value or from good circuit under test. You compare the transitions rather than comparing the output. Okay. And what you expect is the transitions and the match on both the functioning circuit as well as the good circuit, for circuit under test and the good circuit, you assume that the circuit is functioning correctly. Okay. Or with the stored expected value, if the number of transitions are same as the expected value, again you say that the circuit is functioning correctly. But please remember one thing, all these techniques that we are talking of, later on we will talk of some other techniques for signature analysis. When you start doing such type of things, you are reducing the result vector is being reduced. There is a certain result vector, there is a result vector that you wanted, and you are compressing this result vector into fewer number of bits. So the information, so what you are doing is, this is the space of the result vector. So there is only one of them which was actually the correct result vector. This was the pattern which was the correct, but all these were wrong. Now I have a compressed result vector. So when I am taking a compressed result vector, multiple results are going to map onto this. Okay, so this is a function which is mapping multiple result vectors into one result vector, compression basically. Okay, data compression, because instead of storing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 bits, I am going to only store 4 bits now, because actually, okay, 5, it should be 5 bits, because the number of transitions, if this alternate, okay, so 4 bits. Maximum number of transitions can be 14 depending on how you count the ends. So you need 4 bits to store this, and if you use this 4 bits to store information, so 13 bits, so I could have 2 raised to power 13 possible result vectors and only one of them was correct. But here I can only have 2 raised to power 4 possible result vectors and only one of them is correct, but multiple elements of this particular set will map to the correct, and this is called aliasing in testing. So this aliasing results in, so any other pattern which will also have another pattern which also have the same transition count of 6 will also, I will declare that particular circuit also to be correct, but that is actually a faulty circuit. So this will happen in all such things, only have to be, this is to be controlled in the sense that you know that what is aliasing that is happening, and this mapping should be such that not too many map onto this, because if the aliasing increases beyond a certain level, then the confidence level of your testing goes down. Though you may get the same output, but you cannot really be very confident that, because it all depends on what are the probability of these faults. If this is, let us say these two map onto this, is whatever is the probability of this particular fault is. So I have to reduce my confidence level by the probability of this particular fault of my testing. Okay. So, that is as far as the transition count is concerned. Now, let us go to the two methods which are very popularly used today in designs, and we will consider one today, and we will just give an introduction and talk about it in the next class. Scan based testing is a very popular and it's now more or less the standard for a large number of circuits. Primarily in scan based testing, the testing method that is used is primarily a combinational circuit testing method. What you do is you consider the sequential circuit as a set of combination circuits, and for combination circuits you can generate your test inputs by using fault simulation and D algorithm that we have talked of in the previous classes. You can use that to generate the test inputs required for any combination circuit. What do you use this flip flops for? Of course, there are sequential circuits and there are flip flops. One thing is you have to make sure that each of the flip flops is working fine. The only thing that we try to ensure there is that each flip flop can be set to 0 and set to 1, like it actually toggles, like it is possible to for the flip flop to take a value of 0 as well as take a value of 1. So, this is ensured in some manner. We will say how it is done. But to do all that, I do not use the paths that are provided by the circuit. I make a special path which is called the scan path. The scan path is basically nothing but cascading of all the flip flops that are present in the circuit. All the storage elements in the circuit are accessible sequentially using this scan path. So, I form a scan chain. This is called a scan chain for all the storage elements in the circuit. Use this scan chain for inserting the test patterns as well as reading the results. We will see how it happens. Use combination circuit test pattern generator methods for generating test inputs. Let me take a typical circuit and see how. So, a typical sequential circuit, a system, subsystem or a system design looks like this. You can always put any circuit in this form. You cluster all the logic that is between the flip flops and call that to be logic. There could also be some feedbacks. Some of these could also be coming as inputs over here. Outputs could be coming as inputs. This input can be going as inputs. All that is possible, but that is not really important over here. So, you have all this logic, and this is your regular circuit. So, outputs are coming, inputs are coming, they are feeding some logic, they are going to some other set of flip flops or register, then their logic then. What I am showing in the dotted lines is the scan path. So, this is the scan. I cascade all of them. So, if there are multiple flip flops within this register, these flip flops are also cascaded. So, I cascade all the flip flops. So, basically the whole thing, all the flip flops that are present in the circuit becomes a single serial shift register. One single serial shift register with. Okay, actually what happens in scan path is sometimes you also make multiple serial shift registers, not always single serial, but we will talk about here with a single serial shift register, which is a simple scheme. Okay, I should have done. So, I have a single serial shift register, and how do I use my serial shift register? What I do is, I want to test this logic. I generate, so I just consider this to be a combination. This is purely a combination logic. I can generate the test vectors for this. I know what the results it should provide. So, I generate the test vectors for this. So, let us say I have one test vector. Let us say it is a 4-bit test vector 0 1 1 0, and output that I require is, let us say, a 3-bit output which is 0 0 1. There is a combination logic. So, there is a specified test input and specified. I push in this test vector serially to the proper inputs. I will push in 0 1 1 0 through this. I will give specified number of clocks so that this actually reaches this point, and this acts as an input to this logic, and output will be stored over here. There is a clocking mechanism also for testing, very similar to the clocking in this, and I get the output over here, and once I get the output, I give enough clocks, serial shift clocks, to shift this out of this, so that this 0 0 1 that come here over here actually shifts out, and I can perform a check over here when it comes out whether what is the output that came was 001 or something else. If it was 001, that means that test was successful. Once I have done it, I will apply the next test pattern. And when I apply the next test pattern, I will do the same push in the test pattern over here, get the result of this logic and then shift it out and do that. Of course, a lot of overlapping is possible. It's not that each time you have to shift in the whole sequence and shift out the whole sequence. A lot of algorithms exist so that you can perform this in a fewer number of clocks, the amount of, but still it's fairly long because there are a lot of flip-flops in the circuit and certain overlap. So once I have applied all my test patterns and tested this logic, then I have test patterns to test this logic. When I am testing this logic, I have to give longer number of clocks to feed the input. In the previous case, I had to have longer number of clocks to, more number of clocks to get the result. In the second case, when I am testing this logic, I require more number of clocks, shift clocks to feed the input. Why I am doing this? The reason I am doing it is not possible to control through the normal logic. If I want to actually set this register to some value, some pattern, to actually get that pattern through the functioning of the circuit may be very difficult. It's like generating a homing sequence for a vector through a very complex set of logic. It's not just a pure state machine. There are a lot of data paths. There could be a multiplier sitting here. There could be a adder sitting here. To actually give the proper inputs to these components so that actually I get the proper test input for testing this logic is going to be almost impossible. So that's not the way one tries to do it. One only separates out the sequential part and the combinational part. So the only other thing that needs to be tested in the sequential part is that each of the flip-flops actually can take values zeros and ones. And this is done simply by feeding in a 010101 pattern into the input and looking whether the same pattern comes at the output. So if you give this alternating pattern, okay. There are certain drawbacks here, one should also be aware of it. The two things that happen over here, of course, apart from the fact that if you have a lot of test vectors, then obviously the time to test is going to be fairly large, because each time to push in the test vector to the proper register or the proper set of flip-flops, then get the output, then there is going to take, and then reading the result. Some overlaps are possible but only limited. So that's going to take time. Apart from that, when you are testing the flip-flop, you are not using the same path as the path that is used for the functioning of the circuit. So you actually have created another path. So the flip-flop actually may show that it is going 0 and 1 because actually the flip-flop can toggle, the flip-flop logic inside can toggle, but there is a problem at the input over here. That's not going to be tested, at least not in this mode, whether it can take, because your test patterns may, if let's say all of them happen to be that only they take a value 0 on a particular output, so that output the flip-flop is not going to get tested. So flip-flop, because in the scan mode you are having a slightly different logic, and sometimes for the scan mode you also have to have a different clock because you want a full control over the clock at what time I want to latch it. So you sometimes work with two clocks, sometimes actually the same clock is also used depending on how the scan chains are made. But still this is a very, very effective way of testing, and it's predominantly this is the method that is used for testing today's circuits, and there are a lot of standards around scan based. So how do we and there are also typically, if you look at libraries which are used for design, there is also flip-flops which are called scan flip-flops. So what this scan flip-flops essentially mean is they provide you all these facilities for serial data transfer. Apart from, so they provide you the ports by which you can connect the flip-flop sequentially, and even if there is a different clock required or the clocking input to be able to do that. And the reason all these things are chained together are primarily from the point of view of reducing the number of pins. I don't want, for testing purposes, as I said, I don't want large overheads. I want to push in, of course in slowing it down because I am going to push the data serially, but then I only need one pin for pushing in the data and one pin for reading out the data. Sometimes you do a trade-off, you use not just one pin, maybe 2 or 3 pins, so that you can reduce your scan chain. If there are, let's say, 1000 flip-flops, you can divide it into 2 parts, 500 flip-flops scanned from one input, 500 flip-flops scanned from another input, so that you can, your length, the testing time can reduce, but then you have a slightly more overhead in terms of the number of pins. So that is the way the scan based testing works. Now I will just give you a small hint how, for example, we are going to adopt it to the most popular testing method today, which is called signature analysis. We will discuss this in. The signature analysis is related to, typically almost all built-in self-test circuits work on signature analysis. What is done over here is, instead of pushing in a test pattern, you convert these registers into pseudo-random sequence generators. You have a testing mode, whereas these registers, which are input to some logic, act as random sequence generators. We will see how that can be done. And these outputs, this is also a random sequence generator, but the transitions it is performing, the numbers that it is generating are modified by the outputs that are coming over here. So you apply some fixed number of test inputs over here, let us say 10 test inputs. So these 10 test outputs are going to modify the number that is going to result over here, and that is called the signature of the circuit. Okay, I think we will discuss this with an example in the next class, but primarily it is a modification of the technique that we have discussed.